is on that line. So we take that regression equation, plug in the land surface temperature, it calculates a DT, and it calculates your sensible heat flow. I know what you're saying to yourself, well, what about the stability of the atmosphere? So you're absolutely right, we have to correct for that. I won't go into all the gory details, but basically if the air is warm, it goes up. If the air is cold, it goes down, and that's going to either increase or decrease your sensible heat flux. So to figure out whether it's unstable or stable, you plug in that sensible heat flux that you calculated. We already know U star and surface temperature from before. You calculate this Monin-Obukov length, and based on that, we apply different equations to develop these correction coefficients for the movement of heat and the movement of water away from the surface. So we use those correction coefficients, we plug them back into the original equations, and it goes back through and recalculates everything. You calculate your RAH, that calculates H, you plug it back into L, calculate new correction coefficients, and the process iterates over and over and over until the values stabilize, which is about 10% change from one to the next. And then you know that's your corrected sensible heat flux. You can see there's a lot of steps that needed to be automated, and least of which was the pixel selection. So now that we have our incoming radiation calculated, we know how much was used to heat up the air, we know how much heated up the ground, the leftover radiation was used to evaporate water. So now we know the evaporative fraction, and that's instant, only at the instant of the satellite overpass, we know that evaporative fraction. But you can scale it up to the rest of the day by multiplying by how many seconds there are in a day and that radiation. And this is your final output, the ET in millimeters. 10.5 is kind of high. That was before I improved the process. It's much closer now. So to see if I was right, I wanted to validate, and we only, like I said, we only had that one meteorological station at Ekersat, and it actually lies outside of the basin. So we wanted to compare their pan evaporation measurement to these small lakes nearby and see how close Seaball could predict evaporation from the lakes compared to the pan evaporation, which is basically a big bucket. And it turns out it was actually pretty close. Those R-square plots came out a little weird, but the R-square values were fairly acceptable. You can't really see how it tracks, but trust me that it tracks the blue line, that's the pan evaporation, fairly closely. The thing that was odd was we thought basically at this is the end of the monsoon season, so it just rained for 3 months, and then it goes into basically a 6-month drought until May when the rain comes in again. And I thought that ET would be the highest following the rain, and then it would slowly dry out. And it was actually the exact opposite. It kind of fell, it dried out for a little bit, and then ET actually started rising towards the end. So we think that it might be more the radiation and not the water limiting the evaporation, which could be going on. So our expected results was during a drought year, since you don't have as much evaporative cooling, you think the land surface temperature would be much higher. You'd expect NDVI, which is an index of vegetation, to be lower. You have less rain-fed vegetation and lower ET. However, the blue line is the normal year, and the red line is the drought year, and they were pretty much the exact same. The normal year was almost hotter in many time periods. So what we thought would be the most evident drought effect just wasn't there on the scale of the whole basin. So it kind of goes back to the original question. When I first saw it, I was like, well, that doesn't make any sense. How can I change it around? And it turns out, well, I think I'm actually right. At the scale of the whole basin, you don't see much change. It's more on the scale of subbasin to subbasin that you would see the change in drought. The NDVI was a little more clear in showing the drought effect. The max NDVI you would expect to be the same because they're irrigating some part of the basin. So at least some part of the basin would have a really high NDVI. But the mean NDVI in the normal year was higher through most parts of the year, not all the time. And then the C-ball ET was pretty much the same, almost higher in the drought year, which was unexpected. I thought if you have a big drought, the whole basin should be slightly drier and not evaporate as much, but it wasn't the case. So I wanted to look at what was really driving the model. What is the main part of the model? And sure enough, it was the net radiation. That's what drives evapotranspiration. And so evapotranspiration and the ET and the net radiation were pretty much exactly the same. The R-squared wasn't completely one-to-one, so it does mean that that whole complicated modeling process did change a little bit. You can't just take the solar radiation and calculate the T from it, but it's pretty close. So that made me think, okay, if it's net radiation that is really driving this process, why was the ET just as high in the drought year as a normal year? And it turned out that net radiation was actually higher in the drought year. And I'm not sure if that's some effect of the satellite imagery. Maybe it was clearer, less, I don't know, atmospheric moisture, so you get more sunlight in during the drought. Not really sure what was going on there. And I looked at the pyranometer data, which just measures incoming solar radiation on the ground, and it said the exact same thing. So it kind of backs up the whole results of the C-ball. So my main conclusion at this point of the study is that the drought effects aren't evident at a whole basin scale, and it's probably more of those sub-basin interactions. So the next step is, in addition to some extended validation, to see, okay, if we subset by, this sub-basin, there's about 12 sub-basins, which one was most affected by drought? Are you better off being upstream as a basin, being in a smaller one, or are you better off being downstream where you can draw more water from upstream? So it's at the sub-basin scale, we're not sure. We're thinking probably in the middle is the worst place to be because you get it. You're downstream and you're in a smaller sub-basin, or you have a smaller area to get water from. And then I also want to look at a few irrigation projects and see if you get a lot of downstream decay. Because in a normal year, the upstream users, the ones kind of like right at the mouth of the dam release, they tend to over-irrigate, they use more than their share, and not as much goes down to the tail ends. And there's some evidence that actually in a drought year, it's more evenly distributed. Because kind of if you're used to 10 millimeters and you drop down to 2, that's a big change. If you only get 2 all the time, you still get your 2. It's not a big difference. So it could be that the people who use the most irrigation are the most vulnerable and will be the most impacted. So the next step is we do have water balance data from one of these areas for the Nagarjuna-Sagar irrigation district. It's towards the end of the basin. So we can validate a water balance based on how much went in, how much went out, the leftovers, ET, and do a better validation, not just against open water evaporation, but over some land surface areas too. And then analyze each irrigation and sub-basin scale. The only problem is those cloudy pixels. If you have a cloud, it obscures your land surface temperature, you don't get that pixel. So not every image is that perfectly filled in basin boundary. So there's some interpolation methods that can be used, and that's pretty much the next step of where I'm going with the project. That looks pretty good. 18 minutes. Does anyone have any questions?